Welcome to The Explainer. Today, we are diving into one of the coolest tools in all of chemistry. Seriously, this is a technique that lets scientists read the hidden language of molecules, and we're going to learn how they do it.
Okay, just picture this for a second. Let's say you're a chemist. You mix some stuff together, you run a reaction, and voila, you've got this clear liquid. You're pretty sure you've made something brand new, something that's never existed before. But how do you know? How can you prove, down to the atom, exactly what you've made?
Well, they read its secret code. A chemist will take that liquid, put it in a machine, and get back a chart that looks, well, like this. Now, to you and me, it might just look like a bunch of random spikes and squiggles, right? But to a chemist, this is a blueprint. It's the molecule's unique fingerprint. It's called an NMR spectrum, and today, we are going to learn how to crack that code.
All right, let's get into it. To understand the code, we've got to start with the physics behind the signal. And don't worry, it's actually pretty cool. It all starts with the atoms themselves.
So it turns out that some atomic nuclei, and we're going to focus on hydrogen because it's everywhere in organic chemistry, have this quantum property called spin. Now, the best way to think about it is that each hydrogen nucleus is like a tiny spinning magnet. Just imagine a microscopic compass needle. That's pretty much what we're dealing with.
So how does a giant NMR machine take advantage of these tiny little magnets? Well, it's a really clever three-step process. First, you put your sample inside this ridiculously powerful magnet. I mean, huge, and that forces all those tiny compass needles to line up. Then, step two, you blast the sample with a pulse of radio waves. It's just enough energy to knock them all sideways. And finally, step three, you just listen. As those little magnets wobble back into alignment, they give off their own tiny radio signal. And that signal, that's everything.
And here is the absolute key to this whole thing. Not every hydrogen atom in a molecule is created equal, right? Depending on its location in the structure, each one feels that giant magnetic field just a little bit differently. And because of that, each unique type of hydrogen sends out its own distinct signal. The machine picks up all these different signals, and that's what draws that chart we saw, our spectrum.
Okay, so our spectrum is basically a collection of signals, and to solve the molecular puzzle, we need to look for three different clues in those signals. So let's start with clue number one, the signal's location. This tells us all about its neighborhood. So where a signal shows up on that horizontal axis, we call it chemical shift, is all about the proton's local environment. See, every proton is wrapped in a little cloud of electrons. If that cloud is thick and dense, it kind of acts like a shield, protecting the proton from the big magnet. That makes its signal show up at a low number. But if it's next to something like an oxygen atom, which loves to hog electrons, that cloud gets pulled away. The proton is now de-shielded, it feels the full force of the magnet, and its signal shifts to a much higher number. And what's just incredible is how consistent this is. I mean, chemists have been doing this for decades, so there are huge databases of this stuff. You see a signal pop up between 0.5 and 2 ppm, bam. That's almost guaranteed to be a proton on a plain old carbon chain. See something way down around 9 or 10? That's screaming aldehyde group. This first clue is basically like identifying the parts of speech, the nouns, the verbs, in our molecular sentence.
All right, so now we know what kind of protons we're looking at. But the next big question is, how many of each kind are there? And that brings us to clue number two, the molecular head count. So the machine doesn't just tell you where the signal is, it also measures how big it is. Specifically, it calculates the area underneath each peak. This is called the integral. And here's the magic. That area is directly proportional to the number of hydrogens creating that signal. Now, it won't tell you there are exactly 3 hydrogens, but it will tell you the ratio between the different groups.
A perfect example is good old ethanol. It's got 3 different kinds of protons. There's 1 proton on the OH group, 2 protons in that middle CH2 group, and 3 protons on the end CH3 group. So when you look at the integrals for its NMR spectrum, what do you see? A perfect 1 to 2 to 3 ratio. It's a simple, elegant way to count up the atoms in your molecule.
Okay, our third and final clue. And honestly, this is the most powerful one. This is the real game changer. If signal location gives us the words, and the intensity tells us how many of each word, then signal splitting, well, that gives us the grammar. It tells us how all the pieces are connected.
It all boils down to this beautifully simple idea called the N+1 rule. Basically, protons can feel the magnetic fields of their immediate neighbors, the protons on the very next carbon. They're eavesdropping. And the rule is super simple. A signal gets split into N+1 peaks, where N is just the number of protons on the next door atom.
Let's walk through it. It's easy. So if a proton has 0 neighbors, it's all alone, then n is 0. 0 plus 1 is 1, so its signal is just a single sharp peak. We call that a singlet. Makes sense.
Okay, what if it has 1 neighbor? Well, n is 1. 1 plus 1 is 2, so its signal gets split right down the middle into 2 peaks. We call that a doublet.
And you guessed it, if it has 2 neighbors, n is 2. 2 plus 1 is 3. The signal becomes a triplet, 3 peaks, with that middle one being twice as tall. This pattern is literally telling you exactly what's next door. It's like the molecule is talking to you.
And this is where you start to see these really beautiful classic patterns. Take an ethyl group, that's a CH2 stuck to a CH3. It's everywhere in chemistry. The CH2 has 3 neighbors on the CH3, right? So its signal is a 4-peak quartet. And the CH3? It has 2 neighbors on the CH2, so its signal is a triplet. Whenever you see that distinctive quartet-triplet combo, it is a dead giveaway you've got an ethyl group. It's unmistakable. Okay, we've got our 3 clues. Location tells us the neighborhood, intensity tells us the head count, and splitting tells us who's next to who. So now let's put it all together and solve the mystery of ethanol, using nothing but its spectrum.
Let's lay out the evidence, detective style. Clue number 1, location. We've got 3 signals telling us we have 3 types of protons. Looks like one on a carbon chain, one right next to an oxygen, and one actually on an oxygen. Check. Clue number 2, intensity. The integrals give us a ratio of 2 to 3 to 1. Okay, so we have a group of 2 protons, a group of 3, and a single proton. Got it. And clue 3, splitting. The 2-proton signal is a quartet, meaning it's next to a group of 3. And the 3-proton signal is a triplet, meaning it's next to a group of 2. They have to be connected.
And here it is, the moment of truth. When you put all of that evidence together, there is only one, literally only one possible structure that fits all the facts. You have a 3-proton group, CH3, next to a 2-proton group, CH2, which is attached to an oxygen that has 1 proton on it, OH. The molecular blueprint can only be ethanol. The code is cracked.
And this isn't just a party trick. From designing new medicines to creating advanced materials, this is how chemists literally see the invisible world of molecules. NMR gives them the alphabet, the words, and the grammar to read molecular stories. And it really makes you wonder, doesn't it? What other incredibly complex stories are being written all around us in the silent language of chemistry, just waiting for us to find the right way to read them?